All right, so now we want to find the electric field, a distance r from a point charge. So if we were to draw a point charge, right there, plus q, we need to choose a Gaussian surface such that the electric field is the same at all points on this surface, right? In other words, we need to choose a surface that's equidistant from that charge. And the only surface that comes to mind is a sphere. Let me draw a better sphere than that. Let me try this again. That'll do. All right, so this sphere is of radius r. There you go, radius r. And remember that the normal to the surface, right, the dA, points outwards in the radial direction at all points. So, for example, right there, we can draw the dA vector, but that's also, right, the direction of the electric field, the same point. So, using Gauss's law, integral or closed integral of E dot dA is equal to the charge enclosed over epsilon naught. This closed integral right here allows us to, since we've chosen our spherical Gaussian surface, to integrate over that surface, right? Thus, the electric field will be equal across that entire surface. So we can pull that out, right? And now we just have the closed integral of the area vector. Right? This is the beauty of Gauss's law, is that if you can choose an appropriate Gaussian surface such that the electric field is equal at all points, you can pull that E out of the integral. And now we're just integrating all of these tiny dAs across this surface, all of these dAs, regardless of where they are or what shape they are, across the entire surface. Well, it's easy because we've chosen a nice, symmetric, and relatively well-known surface object, which is a sphere. So what's the surface area of a sphere? Well, it's 4 pi r squared. There we go. And the charge enclosed. Ooh, what's the charge enclosed? The charge enclosed of our Gaussian surface, there's only one, and that's the charge Q. Right? So Q. And then epsilon naught is that constant. And now solving for E gives us Q over 4 pi epsilon naught r squared. And that's it. What does this look like? It looks exactly like Coulomb's law, right? Which is the electric field, a distance r from a point charge. Well, this is what Gauss's law gives us in, what, 4 lines, right? Simply from geometry and simply from symmetry, right? If that point charge were outside of that Gaussian surface, say if that point charge was out here, right, the net flux into and out of that surface would be 0, right? So we must choose a surface that's surrounding the charge in question, right? Otherwise, our charge enclosed will be 0. Okay?